Another application of using Newton's laws is solving problems involving an inclined plane. Inclined planes are common problems because we use inclined planes all the time. We use them as ramps, we use them as slides to make a playground fun. So let's look at a child sitting on this inclined plane and enjoying a slide. So all of our inclined planes are defined by the angle that they are raised above the horizontal. So that green line again is the horizontal, and the angle is measured above the horizontal. So this child is sitting there, and if this is a good slide, it's probably very nearly frictionless. So let's treat our incline as being almost frictionless. So maybe it's a water slide where it's slippery. And so the forces that would be acting on our person would be free body diagram. Here's a dot to represent the person, and there would be a weight force acting on the person straight down to the ground. Now I'm going to draw that force on my picture too, just so we can see where it would be if it were drawn on the picture. Now there's also a force from the incline here up onto our person, and that is a normal force. And so I'm going to draw that one. So I'm going to draw a dotty dot dot dashed line to represent the inclined plane, and then I will draw a force vector here. It's normal. Remember, that means perpendicular to the surface. So this was our perpendicular to the surface here. So there's a normal force on our person, and there's a weight force on the person. And because friction is almost negligible in this case, then we are done writing all the forces acting on our person. So if we complete this line here for the weight, then I can think of this as being a triangle. So the angle right here would be 90 minus theta, because of a right angle triangle has 180 degrees. I've got 90 here in this corner. This is my unknown angle, or my theta angle here. And then this would be 90 minus theta, which would mean if I were to continue my normal force green line all the way through the inclined plane there, so that it was normal or perpendicular here, if this angle right here is 90 minus theta, and this angle here is 90, that means that this angle right here would be theta. So if I apply that same geometry here, instead of drawing the line green back, I'm going to draw a gray coordinate system axis, and I'm going to label this angle here as theta. So notice that this angle here was theta, this angle here is theta. It's the same angle. One is just drawn on the picture, and the other one is drawn on the force diagram. So now that we have our force diagram drawn, I'm going to decide that this is my x-axis and this is my y-axis. So instead of our XY axis being a typical horizontal is X and vertical is Y, we're going to tilt it just a little bit so that X lines up with the inclined plane. So we want the X to line up with the inclined plane and Y to line up and be perpendicular to the inclined plane. So we've just rotated our axis just a little bit so that the x-axis is on the inclined plane. So now we can sum these forces, and in my new x direction, I sum my forces in my new x direction and they would be equal to max. They're unbalanced. And so now in the x direction, the normal force is only in my new y direction, but the weight force is a little bit y and a little bit x. And this is different from what we've done before. I'm going to come over here and draw my force gravity straight down. I'm going to draw my coordinate system here and here, where this is theta. And now I want to complete my triangle. So we're going to have down and over. And so this is my y component here, and then I have an x component there. And now the x component in this case is opposite of the angle, and so it will be hypotenuse times the sine of theta. So that means that my force in the x direction will be Fg sine theta. And there are no other forces acting in the x direction in this case, so that would equal ma in the x direction. Now sometimes I like to say that the sine is on the slide. So it's the sine component of your weight that makes you slide down the slide. That's what makes it fun. Now if we look at what's going on in our y direction, remember the y component here of the weight is now adjacent to the angle. So the angle is right here, so it's adjacent to the angle. So it would be hypotenuse times the cosine of the angle. And so when you sum the forces in the y direction for our object on the inclined plane, then it would be a normal force in the positive y direction. Notice the normal force is the only force that's in the y direction there. And then there's a negative component because the weight force is pulling down. It's the component of your weight that is keeping you stuck to the inclined plane, stuck to the slide. And so that would be Fg cosine theta. Now, unless there's an earthquake, you're not going to accelerate in this direction. There's no acceleration in the y direction. Imagine sliding down that slide. You're not hopping off the slide. You're not sinking into the slide. You're just sliding along. And so the acceleration is actually 0, and the forces in the y direction are balanced. So this means that the normal force acting on you is equal to Fg times cosine theta. So that's the component of the force in the X direction and the Y direction.